understanding what they've done there, trying to do for the liver what they did for the heart, would go one stage further, and that is to create, for the first time, a series of multi-scale models which are truly integrated in a way that hasn't been done before. The delivery of the multi-scale representation is modular, flexible, and modifiable, as I've already mentioned. The other thing is that it's not just about the model, but it's about how we get there. Undoubtedly, as with any major program of scientific, groundbreaking science rather, you're going to be developing new technologies, you're going to be developing new approaches, you're going to be developing new tools and processes. And in the sense that we're actually doing something which is very different in the virtual liver, because of the multi-scale approach, the chances are that things will be developed that are very different from what is in current practice and will be hugely beneficial to the systems biology community in general and broadly. So it has a huge potential deliverable from that point of view. But perhaps the most important thing, certainly as far as I'm concerned, is that the opportunity here, for the first time in a program which is integrated in this way, to deliver tangible evidence of an impact on unmet medical needs, whether that be in the clinic, whether that be in terms of diagnosis, whether that be in terms of improving the delivery of new medicines in industry. Now, all of the systems biology that's been done thus far has been fantastically successful in terms of real good science and excellent publications, but in terms of genuine impact, what can systems biology do for human health? The evidence and the jury is still out. There's not a hell of a lot there. There are a few anecdotal examples, but in terms of robust, reproducible, reduction to practice impact on this area, it doesn't exist. Certainly not in terms of sufficiently robustly to persuade industry and the like to take it on board much more aggressively. So the network, here we are, at Germany. I'm learning a lot about German geography at the moment. It's a big country, and as you can see, the red dots are the groups that are distributed all over Germany, which presents a huge challenge for a program manager. And learning the German rail network and airlines is a challenge. But anyway, there are 69 principal investigators which come together in 9 defined work packages. The work packages come to a total of 43 million euros, as I mentioned before, and it's over 5 years. So the work packages essentially come together in 3 groupings. Firstly, at the cell level, looking at metabolism, signaling, and cross-linking, and each of the work packages has a leader and a deputy. Some of these characters you will know better than me, but here we are. Both Jens and Hergo are involved in this series of work packages. The second level is beyond the cell, where we're beginning to look at cell-cell communication, looking at components of liver physiology, the lobule, and then ultimately the whole organ. And the final one is where we actually begin to integrate and translate this, where clearly the challenges of integrating the models together and then managing the data and the knowledge and translating them to the clinic are essential components of the deliverables from this novel program. That's what it looks like. It's a bit like a cat's cradle, and it's impossible to interpret all of those networks on the slide. But it demonstrates the interaction that exists between the different work packages, and each of the work package coordinators has identified those interactions in great detail in the program that was proposed, which is 300 pages long. It's going to generate a hell of a lot of information and an awful lot of data, and I think one of the dangers and one of the perhaps misconceptions in terms of defining systems biology, people understanding what systems biology is the question of whether it's just data management with bioinformatics or whether it's simulations and modeling. Now, my view, systems biology at its core has simulation and modeling at its core in a way that data management per se doesn't. We have a huge amount of data, and there are those who will say that they believe that data is actually knowledge. It's not knowledge. We've lost the knowledge in all of the data, and now we need to move forward, as Elliot said, in terms of understanding what that knowledge means in true sense, that information means in real knowledge. The work packages then are designed to move through from cellular through to the clinical translation in this sort of general schema here, building on each level. And underpinning that, clearly, is the importance of data and knowledge management. Not just about databases, not just about getting the information in computers, but actually understanding how to manage that. And critically, and I think Dennis may talk about this, or touch on it in his talk, is putting the new mathematical tools in place to allow the integration of multi-scale from one scale to another, which is absolutely. To make sure that those things are on track in terms of representation in the clinic, each of the regions has a liver expert that will consult and will be available for each of those regional activities to work with those projects in those regional areas to be able to make sure that the science that's being done in the laboratories is going to have clinical and relevance to the human. The challenges, I've mentioned a few of them. Firstly, like many organs, I guess, but particularly in this particularly specialized organ, it's made up of multiple cell types, which talk to each other in different ways. The physiology is complex, the anatomy is complex, although it is in a very structured tissue architecture. Even though I said the opportunity is there to get the data, and get the quantitative data out of this organ at different levels, the acquisition and standardization of that data is going to be a real challenge across the entire network. As we all know, each group has its own idiosyncrasies in terms of doing its experiments and keeping data and records. I mean, one of the challenges of something like this is to be able to create stuff that will get the data in such a way that it's going to be interpretable not just for modelers and fit for purpose for modeling, which is a challenge in itself, but is consistent across the entire network, as are the standardization of protocols to reproduce experiments. Knowledge management I've already mentioned, and the tools for integration, multi-scale modeling, as I mentioned before. One of the key elements here, again, is managing the expectations of the program. As soon as somebody hears this and it gets maybe interpreted in a very superficial way in popular press, then it tends to raise people's expectations of what might be delivered. I think it's incumbent upon us as scientists, as the people that are involved in this network, to say this is what we're trying to do and make it very clear what we're not trying to do and what the model cannot do, as much as what the models can do. And so managing expectations from an entire network is going to be a key element as we go forward. It's big. It's very ambitious. Some people will say it's too ambitious and it's not doable. But I don't believe that's fair. I think that if we're going to go anywhere in science, we have to set ourselves really challenging targets to go for. There's no shame in putting a huge target in front of you, provided you understand how you're going to approach that target. And for me, you know, this is a great example. Nobody could think we could get to the moon. Nobody could think that we're going to be able to do the genome. But as soon as you produce your target of what it is you need to do, and you understand what needs to be put in place to deliver it, then the technology advancements, the software advancements, the tool advancement that's necessary to support that vision and that drive forward is precisely what happens. You're not going to get that advancement in the absence of a clear vision of where you want to go. This was done with the moonshot. That's what Kennedy said. They're doing it not just because it's easy, but precisely because it's hard. Precisely because it's hard, because it's challenging, it's pushing the boundaries, and it's making you understand where you need to go next. And I fully subscribe to that. How are we going to do it? We have an organisation at the top, the BMBF and PT, Project Training Unit, and me as the Programme Director. We have the work package leaders, project coordinators, and principal investigators. We have a dedicated office supporting me as the Programme Director, and we have 3 scientific administrators distributed broadly regionally. We also have a scientific advisory board that works closely with me and with the work package leaders, and will also be available to the BMBF and PTJ.